All right, my friends.
Stop spreading your L on him.
Yeah, what's up?
What do you want?
May I have your attention now, please? Today, I have some more in-depth solubility kinds of topics than what we had yesterday. Yesterday was just a general introduction. The first few problems that you're going to do are very, very elementary and simple, and then you're going to get kind of popped in the nose because there's lots of different things that can be done with solubility, especially now that we've been through other equilibrium topics. You're going to see acid-base problems coming into solubility. You'll see buffer things coming into solubility. So you've got to kind of be on your game to be able to follow up and finish these kinds of problems. So let's go to a familiar topic that we've learned before. And that would be the common ion effect. The common ion effect is it's a process where you will try to produce something in an environment where there already is some of it. In this case, we're going to try to dissolve iron hydroxide, but it's going to be into a solution where there already is some hydroxide, so there's already a common ion present. And if we remember back to the buffer chapter, when there's a common ion, it doesn't allow the reaction to go as much to the right because you're going to get to equilibrium sooner when there's already some there. So I'll give you a second to copy that down if you want to. So of course I have the ice table covered up, and if I just bring this down, my zero is kind of covered up too. We're starting with 0 of iron ion in the water, but in the water already has some hydroxide. It's a small concentration. It's actually acidic because the pH is down below 7. But that does mean that there's an initial concentration of hydroxide. Now, this reaction is going to go to the right. It's not going to go much to the right. And the fact that there's already some hydroxide there means it's going to go even less to the right. But it is going to go to the right. So it's going to go down by some amount of the iron hydroxide. And remember, this thing right here, the amount of the iron hydroxide changes and produces those products. That's what the solubility is. That term, well, I put a box around that because that's our answer. When we solve for x, that's it. The amount of the solid changes. When that goes down by x, that's going to go up by x, and that's going to go up by 3x. So at equilibrium, this is a solid, so it doesn't have a defined concentration. That has a concentration of x. What is the equilibrium concentration of hydroxide?
So just 3x.
1.0 times 10.
Does this matter?
He circled it in the past.
Yeah, so, okay, so let's assume that it matters because the teacher circled it. What would it do for us?
It will keep the
What is the job of a buffer? Go ahead.
keep the pH constant.
It keeps the pH constant. That's why we use buffers. So if the pH is supposed to stay constant, what does that mean about that number?
It won't change.
It's just going to be the same. So even though the reaction is going to try to produce some hydroxide, because it's a buffer environment, the weak acid that's in there is going to gobble up any added hydroxide to keep the pH constant. Yes?
And would it be also because that since the KSP is so low that it's nothing compared
You want to
to
neglect it? Yeah. Now, this is a really small initial concentration. It might not actually follow the 5% rule.
Yeah.
But since it's buffered, that's why we would neglect it. So buffered means that it's going to be 1.0 times 10 to the negative 9th molarity at the end. There's something in the solution that's going to chew up the added hydroxide to keep the pH the same. Yes?
But if it didn't say buffer, then you would.
You would have to use that number plus 3x. Yep. So what?
It's negligible, that like 3x.
Well, it actually, it's not negligible. It gets consumed because of the fact that it's buffered. So any added hydroxide in the solution, a buffer has a weak acid in its conjugate base. There's some weak acid in the solution that's going to gobble up that and react with it to keep the pH the same. So do the math now. The K value is given to us. It's 4 times 10 to the negative 38th. And that's equal to x times 1.0 times 10 to the negative 9 cubed. Don't forget to cube it. And then this is very simple. To solve for x, it's just going to be that number, the 4 times 10 to the negative 38, divided by 1 times 10 to the negative 27.
Wait, would it be only one sig fig now?
You're stuck with 1 sig fig. Yep.
Wait,
That's fine. This number is ridiculously small, so it's okay to have 1 sig fig. Got a question, or you just stretching it? All right, so the x value, which is our answer, remember we're looking for the solubility, and we're just now finding it, is going to be 4 times 10 to the negative 11 molarity. That's how much that would dissolve. Now, if we hadn't started with any hydroxide, the solubility would be a little bit higher. I mean, we're talking about tiny numbers, but it would be a bit higher. You okay with that? All right, let's take a look at another common ion problem. Just like last time, we're going to calculate a solubility, so that x term under the solid. Can I give you a few minutes to try to do this one? See if you can come up with what the solubility of this is. So we're not dissolving calcium phosphate in water. We're dissolving it into a phosphate solution. So we already have some of one of those ions there. up with something? In the last 2 hours, I've had a lot of people just making mathematical mistakes, arithmetic kind of mistakes. Now let's see how we do with this. That's what our setup should look like. I've had people in both hours today say that 3 cubed equals 9. Ah! Nope. Now, I won't ask if anybody in here did, but I bet somebody did, and it's fine. I mean, you won't do that again, I don't think. Just be careful, those exponents versus times, you know. The plus 2x, can we neglect it? If you don't neglect it, it's going to be x to the 5th power, and you're going to try to solve for it. I'd rather not. Do we know that x is going to be small?
Yes.
Look at that k value. X is tiny. So I think I'd rather just neglect the plus 2x. But Girish, you use it. Keep it in there if you want to.
I don't know the other one we did it. Why do we use it for the first one?
We got rid of it in the one before, too. Not for the same reason, though. We didn't neglect it because x was small, although we probably could. But the reason we got rid of it was because the reaction was making some hydroxide. But because this is a buffered solution, remember what a buffer does. Any more hydroxide that's added gets gobbled up by the buffer so the pH stays constant. So that's why I just took it out. I didn't even put plus 3x into here because I knew that the final concentration of hydroxide, because it was buffered at pH of 5, is going to be the same as it was before. This case, it is going to make some more phosphate, which is going to be present, but it's such a tiny amount that we can just neglect it, compared to 0.2. All right, so I believe when you solve for x, you're going to get, I'm just going from my memory, 2.3?
1.2.
Boy, I got 2.3.
2.3 times 10 to the negative 11,
Yes.
I believe.
Yeah, I tried to do it too.
All right, so I'm pretty sure that's what it is. You're going to take the k value, 1.3 times 10 to the negative 32nd, divided by 27, and divide it by 0.04, that's 0.2 cubed. Then take that answer and take the cube root of it. Yes?
You just always leave that out if there's like something added to it and something that's like.
Okay, now, can we always just neglect the added amount? You know, when we were